Hi guys, welcome to 9.3. What we are going to do today is change our indefinite integrals into definite integrals. And what that means is we are going to be taking antiderivatives, but now if you'll look at our integral symbol, we do have the two numbers. What that means is once we find our antiderivative, we go to the fundamental theorem of calculus to actually go ahead and find a value. And remember what that value represents is the area underneath the curve. So if you were to graph this and start at 0 and go to 1 and section that off, our solution is what the area would be underneath this curve between 0 and 1. Okay, so it's the same idea. We're looking at integration by substitution, integration by parts. So you'll have to figure out which method to use. And then we'll go one step further and re-implement that fundamental theorem of calculus to figure out the area. It's kind of fun. Let's go for it. So the first thing you want to do is figure out, do I use integration by substitution or by parts? And so typically when I look, if I can see like a composition of functions, I right away try substitution. And so what I see is that I do have an exponent of 5. So if f of x was x to the power of 5, then g of x would be x squared plus 1, and the derivative of x squared plus 1 is 2x. So everything is there for me, so I can use substitution. So that's the method I'm going to go ahead and use, okay? So f of x is the outside function, so x to the power of 5. G of x is the inside, x squared plus 1. Now you take the derivative of g of x and we get 2x, and the cool thing is that matches. So I know I don't have to add another value on the outside. With substitution, you're looking for the antiderivative of f of x. So if I add 1, it would become a 6. Divide by 6, so it's 1 over 6 to the power of 6 plus c. Remember, substitution is your antiderivative of f. You plug in g of x, and then you always have your plus c because we're doing an antiderivative. So I have 1 over 6. Where x is, I fill in x squared plus 1. That's to the power of 6 plus c. Okay, now there is your antiderivative. So in 9.1 and 9.2, you got to stop right here. But now that they're definite integrals, we want to know the area of this between 0 and 1. So remember, you take this function, your antiderivative, you fill in a 1, find out the value, fill in a 0, find out the value, subtract them. So if I fill in a 1, I would have 1/6 times 1 squared plus 1 to the power of 6 plus c, minus, if I fill in a 0, 1/6 0 squared plus 1 to the power of 6 plus c. So order of operations, you always go in the parentheses first. So 1 squared is 1. 1 plus 1 is 2. 2 to the power of 6 is 64. So I have it to there. Now I go to the next one. In parentheses, 0 squared is 0. 0 plus 1 is 1. 1 to the power of 6 is 1. Okay? Now what I'm going to do is go ahead and multiply. 1, if I can't, I have 1/6 times 64. I can cross cancel because what I can do is I can divide them both by 3. Oh, no, I can't. Here we go. I have 64, my bad. I'm jumping ahead here. 64 over 6. I'm just going to keep it like this. And you'll see why in just a minute. I looked ahead. 1/6 times 6. 1 over 6 times 1 is 1/6. So the reason why I decided to stay, I wasn't going to start cross canceling and go ahead and do that. But here I can see that I'm subtracting, and I do want a common denominator there. Okay, so c minus c cancels. 64 over 6 minus 1 over 6. Your common denominator is a 6. So back here when I started trying to cross cancel and simplify, I looked ahead and said, whoa, wait, I'm going to have to subtract those fractions. In order to subtract fractions, I wanted to keep that 6 for now. Okay, so I hope I didn't throw you for a loop there. So I kept the 6. When you're subtracting fractions, remember what you subtract is the numerator. 64 minus 1 is 63. Now here's where I'm going to go ahead and divide top and bottom by 3. I can reduce this. 63 divided by 3, I get a 21. 6 divided by 3, I get a 2. So that tells us that the area of this curve in between 0 and 1, if you were to actually graph it and shade it and count up the little squares, you'd have 21 over 2, which is 10.5. Kind of cool. So it's just kind of putting everything together for the end of the year. And you are hearing me correctly. We have this section and one more, you guys, and that's it. And then we'll take our test and our final, and we'll be done with calculus. So it's kind of sad. All right, let's go on to number 2. Now, number 2, I don't see a composite function at all, because this is the cosine of x. If this was like the cosine of x squared or 3x squared or something like that, that would kind of, be a little hint maybe to try substitution. But I don't see any compositions here. So I'm going to go integration by parts, because this resembles the product rule. This has a variable, this has a variable. So f of x equals x. It's the first term. G of x, our second function, is the cosine of x. When you're doing integration by parts, I want the derivative of f of x, that's a 1. Then I do the antiderivative of a cosine. The antiderivative of a cosine is a sine of x plus c. Now remember, integration by parts, the formula is you take your original f of x times the antiderivative of g of x minus the integral of the derivative of f of x times the antiderivative of gx times dx. This just means that we know we are calculating another integral within the problem. Okay, so if I go ahead and I do this, f of x times the antiderivative x times the sine of x is x times the sine of x minus the antiderivative. Now this is a 1. 1 times the sine of x is a sine of x dx. And that's what I had to do here, is take the derivative of f of x. That's just a 1. 1 times the sine of x is a sine of x. So I have x times the sine of x minus the antiderivative of a sine of x is a negative cosine of x plus c. If I'm minusing a negative, this turns into a plus. So you guys, here's my antiderivative. I'm done with that part. So it's x times the sine of x plus the cosine of x plus c, antiderivative. But because it's a definite integral, I need to go from 0 to pi over 2. Now notice, this is in radians. So if you remember that unit circle, when you go around the unit circle, they give you 2 options for measurements. One is in degrees, the other one is called radians. And radians is when you see things like pi over 3 and pi over 2 and 3 pi over 2 and 5 pi over 4 and all those super fun things. So knowing that I'm going to pi over 2, right now is a good time to take that calculator and make sure that you are in radian mode. Okay, so again, you hit DRG. This means degrees, this means radians. Before we calculate this, you want to make sure that your 3 little lines are underneath radians, so you know that you are in the correct mode of the calculator to make this calculation for pi over 2. Okay, so I have fill in your antiderivative pi over 2 minus fill in a 0. So I'm going to go ahead and just calculate this. So I'm going to put my pi over 2, I know what's in my radian mode, pi over 2 in parentheses. So pi divided by 2, okay? That's what x would be. Now multiply by the sine of, it opens a parenthesis for you, pi over 2, plus cosine of pi over 2. And when I hit enter, I have 1.570, so I'm just going to say, I know it's approximate answer because I am rounding, but I'm just going to go the 1.57 because that is where I got a 0 right there. Minus, now I'm going to go back and put in a 0. 0 times the sine of 0 plus the cosine of 0, I get a 1. So if I minus 1, okay, I'm going to go ahead and look at this. Here is my area. 1.57 minus 1 is 0.57. C minus C cancels, and we are done. Okay, so that was it for number 2. I just wanted to make sure that I showed you one that did have radian measurements, just to remind you how to do that on your calculator. Let's go to number 3. Right away, as soon as I see an exponent or a square root symbol, that's typically when you can look at substitution as your process. So if I go ahead and I rewrite this, remember when I first kind of showed you how this works, I rewrote everything just to kind of break it apart for you. Because I have this on the bottom, I can rewrite it as 2 times x squared plus 1 to the negative power of 2. Because remember, if something is on the bottom of a fraction, that means it has a negative exponent, times 12x dx. These two things are totally equivalent. So if one way makes it easier for you, go ahead and rewrite it. For me, personally, I like having the negative exponent because now when I go ahead and I do substitution, because I can definitely see a composition function in here, I know the outside function is x to the negative power of 2. But I'm not just taking an x to the negative power of 2. I'm taking 2x squared plus 1 to the negative power of 2. For substitution, that's where I do the derivative of g of x, which ends up being 4x. The derivative of 1 is a 0. Now hold up, Houston, we have a problem. The solution is really 4x. What we're seeing is a 12x. So we had a 4x, we have to say, all right, if it's 4x, how the heck am I seeing a 12x? That means that you had to have multiplied it by 3. So there's going to be a 3 on the outside because 4x times 3 would get you the 12x. That way it matches. Now, antiderivative. Antiderivative of f of x. It's negative 2. If you add 1, it's a negative 1. Divide by a negative 1, so it's negative x to the negative first power. Or, if you like, you can go negative 1 over x because this is a negative 1. So that means you have 1x on the bottom plus c. Either way is totally fine. So it's whatever you are more comfortable with. Okay, I'm going to go ahead and use this one. Okay, so if I'm doing substitution, remember, here's your formula. It's the antiderivative of f. You fill in the original g of x, and you have a plus c. So I have my 3 on the outside. My antiderivative, it's negative 1 over, but instead it's g of x, which is 2x squared plus 1 plus c. Now I have to remember that I had this 3 here. Remember, when you're multiplying fractions, it's top times top, bottom times bottom. So 3 is the same as 3 over 1. So I have negative 3 over 1 times anything. So if I take 1 times 2x squared plus 1, it's going to keep its identity. It's that multiplicative identity property from way back in Algebra 1. Okay, so if I look at this, this is my antiderivative. But I'm going from 0 to 2. So I have to go ahead and fill in a 2, find out the value, then fill in a 0, find out the value. So I have negative 3 on the top. If I put in a 2, the bottom, okay, just order of operations. 2 squared is 4. 4 times 2 is 8. 8 plus 1 is 9. Minus, if I put in a 0, I know I have that negative 3 on the top. If I put in a 0, 0 squared is 0. 0 times 2 is 0. 0 plus 1 is 1. I forgot the c. There we go. Okay, now when I keep going, I can go ahead and reduce this. So I'm going to grab a separate sheet of paper. Okay, so if I reduce this, negative 3 over 9 is negative 1/3 plus c, minus negative 3 over 1 is a negative 3 plus c. Okay, so now I have it to this point, which is awesome. Right away I see, okay, positive c minus a positive c is gone. So I have negative 1/3 minus a negative becomes a positive. Now this is 3 over 1. I know that what I'm doing here is adding fractions. So I'm going to change this to 9 over 3 because 9 over 3 still has a value of 3, but now I have my common denominator. The common denominator carries. Negative 1 plus 9 is 8. So your area between 0 and 2 underneath that curve is 8/3. And we have 2 more, guys, and that's it for 9.3. So let's keep on going. Okay, now this one, I don't automatically see a composition function. I do see what appears to be similar to like a quotient rule because I do have something with an x on the top and something with an x on the bottom. And that's where integration by parts came in. It works side by side with product rule and quotient rule. So I'm going to go ahead, integration by parts. So f of x, remember when you have a fraction, f of x is whatever's on the top. So 2x plus 1. G of x is whatever's on the bottom, but you have to remember here, it's on the bottom, so the exponent is negative. So this is e to the negative x. That's kind of the tricky part when you do integration by parts. Your g of x, yes, it's what's on the bottom, but you still have to remember to make that exponent negative, indicating that it was on the bottom. Okay, now when you're doing integration by parts, it's the derivative of f of x, that happens to be a 2. The antiderivative of g of x, it's an e term. So remember, you keep the e term the same. So e to the negative x. Now you take the derivative of the exponent, which is -1, divide by a -1. So I end up with negative e to the negative x plus c. Integration by parts is your original f of x times your antiderivative of g of x minus, take the derivative of f of x times the antiderivative of g of x dx. Okay, so I'm going to go ahead, and now this is, when I'm multiplying these two pieces, my original f of x and the antiderivative, there's no pretty way of combining this. So I just went ahead and said, all right, let's take 2x plus 1 times the negative e to the negative x. I just said, all right, let's just put those two things together. Because I know at the end, what I'm really doing is making a calculation, and I'm not going to worry about trying to combine those in a pretty manner so it looks good. Okay, now here I have to take these two things and multiply them. So 2 times a -1, it's a -2 e to the negative x dx. Okay, so I went ahead and I went through the first process. -2 is a constant. I can bring that out front. So I have my original f of x times the antiderivative of g of x, negative times a -2. This is now a plus 2 on the outside, e to the negative x dx. Now it's time to go ahead and find the antiderivative. So 2x plus 1, negative e to the negative x plus 2. This is an e term. When you take the antiderivative, you keep the e term the same. Take the derivative of the exponent, which is -1, divide it, so that makes it a negative e to the negative x plus c. So here is my antiderivative. I'm sorry, positive 2 times a negative e. I almost forgot to combine them here. Positive 2 times a negative e is a -2 e to the negative x plus c. This is my antiderivative, so now I can go from 0 to 1. So I have to fill in a 1, see what the value is, then fill in a 0. Okay, so I'm just going to go ahead and go step by step on this. So if I put in a 1, 2 times 1 is 2. 2 plus 1, so this ends up being a 3. If I put in a 1 here, it's negative e to the negative first power, so I can go -1 over e. Because if I put in a 1, that means that it's negative, it's on the bottom, there would be 1 e on the bottom. Minus, I'm still putting in a 1. So this would be 2 over, if I put a 1 in here, e to the negative first power means I have 1 e on the bottom, plus c. Okay, so that would be my first piece. Minus, now I'm going to put in a 0. 2 times 0 is 0. 0 plus 1 is 1. If I put in a 0 here, negative e to the -0, well, there's no such thing as a -0. So e to the power of 0, anything to the power of 0 is 1. 1 times that negative is going to make it a -1. Minus, same thing here. If I put in a 0, e to the power of 0 is 1. 1 times 2 is 2. Plus c. I'm just kind of walking it through because I know sometimes this is where a few of you got frustrated not knowing how to put the numbers in or how do you correctly put it into the calculator. So that's why I'm kind of going just step by step. Multiplying, this is the same as 3 over 1. So this is -3 over e minus 2 over e plus c. And guys, we can combine this. They have a common denominator. It's e. It's totally fine if it's e. -3 minus 2 more is -5. So here's a simplified solution if you take the antiderivative and fill in a 1. It is -5 over e plus c. Minus 1 times -1 is -1. Minus 2 more is -3 plus c. So ready to find my final answer. Positive c minus positive c cancels. This turns into a plus. Now when you put this on the calculator, I'm going to show you this. So -5 divided by, now remember e is above the natural log, so it's second ln. E is always a base. So when you do that, it automatically puts e to the power of what? Well, if you don't see an exponent, it means that it's e to the power of 1. So this is how you would have to enter -5 divided by e. So it's -5 divided by e to the power of 1. That would be the decimal value. Minus a -3 means I'm really adding 3. So if I go plus 3 to that answer, my solution is approximately 1.16. And you are done. So this one was a pretty good example of how do you enter things in the calculator. What happens if you can't make this look nice? That's okay. Just keep it as the 2 separate pieces. We went through step by step, filled in our 1, filled in our 0, calculated it all the way to the end. Your final answer is approximately 1.16. One more question for you today. Now again, one thing to remember when you are looking at a square root, this is the same thing, you guys, as this. And the reason why I'm showing you going from here to here is because as soon as you see something other than an x with that exponent, right away in your mind it should go ding, 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 substitution. Because that's a composition. My f of x is going to be the square root of x or x to the 1/2 power. Okay, because that's how I get that 1/2. But your g of x, it's not just an x. It's an x squared minus 9. Now, substitution, remember, here's our rule for substitution. So I need the derivative of g of x. The derivative of g of x is 2x. So hold up. We have another problem here, okay? So I know that this is really a 2x here, but I'm only seeing a 1x. So how did the 2x get changed to just an x? Well, there had to have been a 1/2 out front because 2x times 1/2 is how you would just get to the single x. So remember, this is technically what's there. I'm only seeing an x, so I had to have multiplied my 2x by 1/2 to get there. That's kind of the only trick with substitution, is to make sure that you are matching that derivative of g of x. Okay, so I'm going to go ahead and antiderivative of f of x. If I take my 1/2 and add 1, that would be 3/2. Divide by 3/2 is the same as multiplying by the reciprocal, so it'd be 2/3 x to the 3/2 plus c. So here is my formula. I have the 1/2 up front because I had to match my derivative of g of x. Now it's the antiderivative, which is 2/3. Instead of x, I put in my x squared minus 9 to the 3/2 plus c. I can simplify this because I can cross cancel the 2's. So what I really have is 1/3 times x squared minus 9 to the 3/2. Now I can picture some of your work right now. I would say 60% of you would jump from 3/2 and say, hey, that's 1.5. So just in your honor today, I'm going to do that, okay? We're going to go 3.5 or 3/2. We're going to jump to 1.5, okay? Then I can go ahead and do my fundamental theorem of calculus. We're going from 3 to 5. So I'm going to fill in a 5. Then I'm going to fill in a 3 and figure out what those solutions are. The nice thing is this I can enter at one time. So if I go 1 divided by 3, okay, there's your 1/3. So 1 divided by 3, then open another parenthesis. If I put in a 5, it's 5 squared minus 9, close it, to the power of 1.5. Ooh, I get a 21.33 plus c minus. Now if I put in a 3, the only thing I'm changing here is x. So where I had 5 squared, I can just up arrow, change that to a 3 squared. Everything else is going to stay the same because I only have one variable within my antiderivative. So I changed my 5 squared to 3 squared, hit enter. Holy smokes, I got a 0. Okay. C minus C cancels. 21.33 minus 0 is 21.33. So that would be the area underneath this curve if you use the x values 3 to 5 and shade that region. I hope you guys enjoyed 9.3. I miss you lots and I will talk to you soon. Bye.